It was.
Bumped into him after.
Oh yeah, bumped him into him accidentally with his fist.
All right, so you had so much fun in 30-1 proving trig identities. We're going to do some more. Lesson 6.
I love starting in one of
Wait, I can prove sine squared x plus cos squared x is 1.
How?
Just separate the 1 into sine squared x plus cos squared x.
Good job, Ray. Good job.
The formula sheet says it, so
Yeah.
you just put a 1.
All right, so we use previously known identities to prove that a trig expression is correct, true, equal. And if you're asked to prove one, then it can be proven. You won't get any that are not actually true. So you need to transform either the left side or the right side or both sides to get an identical form. And we use other known identities. And in 30-1, we talked about some of the hints that you could use. One of them is if that there's any powers, any squares, look to those Pythagorean identities. So sine squared x plus cos squared x equals 1 is one of those identities. If you get out your formula sheet, you have them all there. But another variation of this is found by dividing every term by sine squared x, which will give you 1 plus cotan squared x equals cosecant squared x. And if you take this identity and divide every term by cos squared x, you'll get tan squared x plus 1 equals sec squared x. So if there's any squareds, normally we look to those Pythagorean identities to see if they would help us out. If not, then we put everything in terms of sine and cos. For example, tan theta can be written as sine theta over cos theta. The cotan then is the reciprocal cos theta over sine theta. So if there are no powers, normally you put everything in terms of sine and cos. And you might use a reciprocal ratio there as well. If there's powers higher than 2, then chances are you got a factor. So those are all some of the things that we did. In some cases, we multiplied top and bottom of an expression by a conjugate. Right? So those are all things that we did in order to prove identity. So for this first one, there's no powers. I'd put everything in terms of sine and cos. Cotan, again, is cos over sine. And that's multiplied by secant, which is 1 over cos. And now because you are multiplying those two together and you've got a cos theta on top and bottom, you can divide top and bottom by cos theta. And you'll get 1s there. So on top is 1 times 1 over sine theta times 1. You'll get 1 over sine theta, which is cosecant theta. Or you could have written the right side as 1 over sine theta and stopped there on the left. It doesn't matter. You just have to get the same expression on both sides. For number 2, again, there's no powers there, so we put everything in terms of sine and cos. You don't have your booklet? Cotan, again, is cos over sine. And that's divided by cosecant, which is 1 over sine. And to divide a rational expression, you multiply by the reciprocal. The sine thetas will cancel, and you're left with cos theta over 1. Remember, when you divide top and bottom by sine thetas, you actually get 1s there. And you multiply top times top, bottom times bottom, you'll get cos theta over 1, or just cos theta, which is what the right side is. Okay, we saw in 30-1 that in many cases it can be done in 2 or 3 fairly simple, straightforward steps. Sometimes we saw ones that required a bit more work, but they can all be done. Looking at number 3, again, no powers there. So we would normally put everything in terms of sine and cos, but also in this case, you got some brackets on the left side to multiply out. Multiply both terms inside the bracket. What are you looking for? Pardon? I can get one for you later. So on the left side, let's see if we can simplify that second term. 1 over cosecant is 1 over sine, and that's multiplied by sine theta, which is sine theta over 1. And then once again, you can divide top and bottom by sine theta, which leaves you with 1s there. And so you have a first term of cosecant theta plus, and then on top it's 1 times 1 over 1 times 1, which is 1. So you get cosec theta plus 1, which is the same as 1 plus cosec theta. And so now we have the same thing on both sides. Occasionally, you have to get a common denominator and add rational expressions together. And that is what we'll need to do for number 4 on the left side. We would put everything in terms of sine and cos. Tangent is sine theta over cos theta, and that's divided by 1 minus cotan, which is cos theta over sine theta. And so that first expression, we can combine these two terms together by getting a common denominator of cos theta. 1 would be cos theta over cos theta. So we'll get cos theta minus sine theta all over cos theta divided by, for that second expression, we would combine those two together by getting a common denominator of sine theta. 1 would be sine theta over sine theta. So it'll be sine theta minus cos theta all over sine theta. And once again, when you're dividing rational expressions, you can multiply by the reciprocal. So that'll be my next step. However, if we compare the top left and the bottom right, those two are not the same. They are opposites. But we can make them the same. If we took out a common factor of, let's say, -1 on either the top or the bottom, I'm just going to use this numerator for that second expression, which becomes a denominator when we multiply by the reciprocal. Take out a common factor of -1. The cos theta will become positive. The sine theta will become negative. And now we have the same expression on top and bottom. We can divide top and bottom by cos theta minus sine theta. And we'll be left with sine theta over negative cos theta, or negative tan theta, I should say. Sine over cos is tan. And now we have the same thing on both sides. All right. Number 5. I've got sine squared theta on the left. On the right, sec squared theta minus 1 all over sec squared theta. So because we see those squareds, we'll see if we can use one of the Pythagorean identities. So we wrote them on the previous page. And If you look at this second one here, if you subtract the 1 from both sides, you'll get sec squared theta minus 1 on the right equals tan squared theta on the left. So that's what I would do. Sec squared theta minus 1 is equal to tan squared theta. So we'll have tan squared theta divided by sec squared theta. Tangent is sine over cos. And that's divided by secant, which is 1 over cos. And again, to divide by a rational expression, we multiply by the reciprocal. The cos squared thetas cancel, and you're left with sine squared theta. So that would be one way to do this. But there are often more than one way to do these ones. So I'm just going to show you an alternate way that we could have done this. Again, working down the right side. You've got a binomial on top divided by a single term on the bottom. What you can do is take both terms on top and divide by the denominator. And so sec squared theta divided by sec squared theta is 1 minus 1 over sec squared theta. So that's asking for the reciprocal of sec squared theta, which is cos squared theta. And from the original Pythagorean identity, 1 minus cos squared theta is sine squared theta. So that's another way we could have worked down that right side to get sine squared theta. Sometimes there is more than one way to do these. Number 6, you've got some squares though, so squares there, excuse me, so immediately you may think about the Pythagorean identities. However, if you recognize that there is a factor of sine squared theta in both terms here, that would lead us to take out a common factor of sine squared theta, which will give us 1 plus cotan squared theta. And if we look at our Pythagorean identities, 1 plus cotan squared is cosecant squared. That's this one in blue here. 1 plus cotan squared is cosecant squared. So it'll be sine squared theta times cosecant squared theta. And cosecant is 1 over sine squared. So the first factor of sine squared theta, I'll write it over 1 times 1 over sine squared theta. And we would divide top and bottom by a factor of sine squared theta. Dividing something by itself gives you 1. So you'll have 1 times 1 on top over 1 times 1 on the bottom. Gives us our 1. Right? This next one, you've got that cos cubed theta as the first term. You also have a factor of cos theta in the second term, so we would take out a common factor of cos theta, which would give us cos squared theta plus sine squared theta. And we know that that is 1. From the original Pythagorean identity, sine squared theta plus cos squared theta equals 1. And so we have the same thing on both sides. So again, a couple fairly simple, straightforward steps. Number 8, not really anything we can do on the left side. And remember, you cannot move things from one side to the other. You can only do that if you know the two sides are equal, and that's the point of these. You want to prove that they are equal. So you cannot move things from one side to the other. You can't square both sides, square root both sides. You can't do any of those things that we used previously to solve equations, because that's only if you have an equation to begin with. These are identities. You want to show that they are true. Once you show that they're true, then you can say they are an equation. But we need to show that. So, number 8. Again, not much we can do on the left side, but we can do some things on the right side. And one of the things that I would probably do here is I would change sine squared theta to 1 minus cos squared theta. That comes from that Pythagorean identity. There's a single term on top over a binomial on the bottom, so you can't break them apart and say it's sine squared theta over 1 and sine squared theta over negative cos theta. You can't do that. You can only do it if you have a binomial on top divided by a single term on the bottom. So by changing the top to 1 minus cos squared theta, you've made it into an expression that you can factor. That is a difference of squares. Remember, a difference of squares is where you have two terms, both are perfect squares, minus sign in between. The square root of 1 is 1. The square root of cos squared theta is cos theta. One's a plus, one's a minus. And now you can divide top and bottom by your factor of 1 minus cos theta. They cancel, and you're left with 1 plus cos theta, which is what the left side is. So again, essentially we did two fairly straightforward steps. And most of them can be done in 2 or 3 steps. You try something, if it doesn't work, you try something else. So number 9, to do this one, I would use the sum and difference identities. The cosine of x plus y is cos x cos y minus sine x sine y. And that is multiplied by cosine of x minus y. So for that one, we'd use the difference identity for cosine. And so we've got two binomial expressions here that we're going to multiply together. So we use a distributive property or FOIL it out. When you multiply the cos x cos y by cos x cos y, that'll give you cos squared x cos squared y. When you multiply those front terms together, the outer products, when we multiply them together, it'll be cos x cos y times sine x sine y, and they're both positive, so it'll be positive cos x cos y sine x sine y. And then when we multiply the inner products together, it's a negative times a positive. It'll be negative sine x sine y cos x. Whoa. Cos y. And then the last terms, when you multiply them together, it'll be a negative times a positive, which is a negative. And you're going to get sine squared x sine squared y. Now, positive cos x cos y sine x sine y minus, even though these factors are written in different order, they're still all the same 4 factors. So these two will cancel each other out. You could rearrange these to be minus cos x, cos y, sine x, sine y. They're factors, and it doesn't matter what order you multiply things in. Order doesn't matter when you're multiplying. So again, these terms cancel each other out. So we are left with cos x squared, cos y squared, minus sine squared x, sine squared y. And I said those first ones wrong. It should have been cos squared x, cos squared y. So I don't have what I need on the left side because it doesn't match what's on the right side. So we need to do some more work. So here's the next thing we'll do. And sometimes you have to do some trial and error. You try something. If it doesn't work, you try something else. Okay. So what I'm going to do here, I'm going to keep this first term the same. But for the second term, I'm going to change sine squared x to 1 minus cos squared x. And I'm going to change sine squared y to 1 minus cos squared y. And my next step is I'm going to multiply out those two binomials. So the cos squared x, cos squared y stays the same for now. I have to subtract all of the product of those last two factors. So I'll put it in brackets to remind myself I got to subtract all of it once I'm done multiplying. And that's my next step, to actually multiply those out. The front terms multiplied together is 1. The outer terms is minus cos squared y. Inner is minus cos squared x. And the last, a negative times a negative is a positive, cos squared x, cos squared y. And now you should see that we're going to make some headway because the minus sign in front of this big bracket changes all the signs inside, which means this last term is going to be cos minus cos squared x, cos squared y, which will cancel with the positive cos squared x, cos squared y at the start. So that'll be my next step. I'll remove the square brackets. The negative sign in front changes all the signs inside. And like we said, those cos squared x, cos squared y terms will cancel out. So we are left with cos squared x plus cos squared y minus 1, which is exactly what the right side is. So that one is done. Okay. So for practice, you can work on those questions. I will post a solution for Google Classroom so you can check those answers. Some of these ones that we did, very similar to the ones we did in 30-1, but some of them went a little beyond that. And we'll do some more tomorrow where we're going a little beyond what you previously did in 30-1. Okay?